Welcome to Logic Heads, the series that is all about digital logic. Exactly what is logic? Where did it come from? Where is it going? In this episode, we'll find out. Because the very best place to start our exploration is at the beginning. So what is this stuff called logic anyway? And where did it come from? Well, actually, it depends on your field of study. For example, if you're a philosopher, logic goes back to ancient times. Aristotle and Socrates taught with examples like this one. There are 4 jugs sitting on a table. One of them contains deadly poison. The poison is not to the left of the tallest jug. The poison is either in the brown jug or the blue jug, and the smallest jug is not safe to drink from. So, which one should you drink from? The answer, of course, is you need to find yourself a better drinking buddy. Now, if you're a math major, logic starts with George Boole from the 19th century. He organized the ideas that logic could be expressed as a mathematical language, which gave us Boolean algebra, on which modern computer science is based. You could sort of call him the father of the 0 and the 1. But this is an engineering class, so we're going to start logic when it got its electrical form. Imagine ourselves in the middle of the 1960s. The vacuum tube has been the king of electronics since the turn of the century. Its diminutive brother, the transistor, has only been around for about a decade. Now, using Boolean algebra, engineers can dream of how to make a complex computing machine that utilizes thousands of these devices. However, they can't reliably build them yet because there's simply too many interconnections between all those devices. There are too many solder joints to fail. What computers need is some new, innovative way to interconnect all the transistors. And the answer is, of course, the integrated circuit. By using photographic methods, engineers learn how to interconnect dozens of transistors together on a single piece of silicon to create the first integrated electronic devices. And the very first of these devices are the logic devices. But it was the NASA moon missions that finally drove the need to create highly integrated, for the time at least, digital computers. Remember, the microprocessor in the memory device won't even be invented for another decade or so. If you want to build an arithmetic unit, you have to build it from Gates. And build it they did. This is a replica of the Apollo guidance computer, as built by John Poltorek. You can find more information on the web. It takes up the equivalent of 4 19-inch equipment racks, but it is absolutely tiny by 1960 computer standards. Its specifications are like this. It has a 1 megahertz clock, 1K of RAM, and 12K of ROM. You probably can't even buy a part that small today, and it would cost a few cents if you could. However, this machine was powerful enough to calculate the trajectories to fly men to the moon and safely return them. And the best part is, it was completely constructed from logic devices. In fact, it uses about 5,000 3-input OR gates, which are essentially the same function found in the 74HC27 device that is still made today. In the 1960s, logic was king because that's all there was. But let's jump up a couple decades into the 1980s. Now, the personal computer has not been invented yet, but there are certainly a number of microprocessor-based systems out there. One of the more common ones is called the S100 system, as shown here. There's that new microprocessor right in the middle of the board. Our friend Logic still makes up a huge amount of the rest of the system, but you can already see the migration. The logic is slowly moving outward from the center of the design out to the peripherals. It's no longer the starring role, but logic is still a critical part of this system. Now let's take one more jump up to modern times. Despite all the rumors to the contrary, logic is still alive and kicking. ASICs and PALs and EPLDs didn't eliminate logic, they simply helped to redefine it. Now this is a modern motherboard. This one happens to be out of the MacBook Air. The processor and the chipsets are highlighted in orange and red, and the onboard memory is inside that yellow block. Now, even at this magnification, you can't even see the logic devices, but I assure you, they are still there. You see, logic has totally redefined itself over time. Gone are the days of the gigantic MSI and LSI logic devices. Instead, most logic is single and dual gates in extremely small packages. And what do these gates do? Well, they help out those big ASICs and SoCs by providing a very cost-effective way of fixing those inevitable engineering changes or oops that occur late in a design. Signals a wrong polarity? How about a very tiny, inexpensive logic inverter to get that signal back the way that you wanted? That's what logic does today. This is the state of the art in logic today. The functions are still basically the same. The NAND gate, the OR gate, the NOT, the exclusive OR. But the semiconductor processing is light years ahead of what was done in the 1960s. A single transistor on a logic device can be less than 0.35 microns or millionths of a meter in width. That's many of orders of magnitude smaller than that first integrated circuit, and many times smaller than a human hair. Now, some microprocessor memories boast even smaller geometries, but for logic, that actually becomes a disadvantage. You see, since there are so few transistors in a logic device in the first place, by shrinking those transistors smaller and smaller, you ultimately get to the point where the piece of silicon is too small to handle. It becomes a grain of sand. In terms of performance, today's logic gates are way advanced from their ancestors. Instead of operating at dozens of volts and amps of current, modern logic devices can operate down to a fraction of a volt and consume only a millionth of an amp, and work faster and more reliably at the same time. But the real innovation in logic devices is in the packaging. Pretty much gone are the original packages, the dual inline package or the DIP. For the amount of silicon they contained, those packages simply took up too much valuable board space. So most simple logic devices are found in the leadless package or the micro pack. These devices are only about 1 millimeter by 1 millimeter in size. Now this happens to be the ultimate in packaging. It's called the diamond pack. With 5 leads, it can hold pretty much any 2-input logic device, but all the space that it needs is less than the size of a head of a pin. In fact, the head of a pin is big enough for this logic device and 3 of its best friends. Some people will ask, how long will logic be around? I think the best answer is, well, it's been around for 50 years already. I wouldn't be surprised if it's still here in another 50 years. Sure, it will continue to evolve and get smaller and more cost efficient. But logic, and thus the logic kit, is here to stay.